Okay.
Okay. Good afternoon. I'm Katie Smith, and this is Scott Brand, and we're going to present our single effect evaporator lab. First, just an outline of the presentation. We'll be covering an introduction, the theory, the apparatus, the experimental procedure that we followed for each week, and the results, data, conclusion, and we also included our references. Scott will talk about the introduction.
Alright, first, evaporation is basically heat transfer to a solution in order to evaporate out the solvent. So you might use this in making evaporated milk, where you would get the liquid out so that way it's easier to transfer the condensed milk to another company and save costs on shipping. The two main factors that influence the design of the evaporator are the economy and the capacity, and those change with feed flow and pressure of the evaporator itself, where capacity is the kilograms of solvent vaporized per hour, and the economy is the kilograms of water vaporized per kilograms of steam feed or whatever you use to heat the solution. And the properties of the solution also affect the design. So density, if you need different design for density or viscosity or anything like that, you could have it in a vertical direction or you could have it in a horizontal direction, depending on your purposes. The other factors affecting the evaporator are the operating temperature and pressure based on the physical properties of the solution. So depending on if you need a higher temperature to evaporate the solvent out, or you can maybe lower the pressure in order to increase the saturation pressure, or so that way the temperature would increase for when it would evaporate.
I'll continue now with a little bit of the theory and the background of a single effect evaporator. As Scott kind of alluded to earlier, the purpose or why you would include a single effect evaporator is to form a more concentrated solution from a more dilute feed. In this case, pure liquid water was our feed, and so our two product streams were liquid water and then the vapor condensate water. The feed was boiled to evaporate off water, which in this case our feed was pure water, but normally you would have some other solvent or some other concentration, maybe ammonia or something else in there that you would be making a more concentrated solution. The temperature inside of the boiler is equal to the temperature of your liquid stream coming out, and also the same temperature for your vapor condensate as shown in figure 1, and this is a figure from our unit operations textbook, and you can see here T1 denotes the temperature inside the boiler as equaling to the vapor product stream and the concentrated liquid stream, which also each have their own composition, X and Y respectively, and their own enthalpy values, the capital H. You can see from the diagram that we have the feed coming in at its temperature with its certain concentration, mole percent, and the enthalpy of the feed. And then we also have steam entering with its own temperature of the steam and the enthalpy of the steam. And the steam also leaves in the condensate at temperature and its enthalpy. So as I mentioned, the temperatures are the same, and this is because the liquid and the vapor are in equilibrium inside of the boiler, and the vapor outlet is condensed by a cooling water system that we had running while we were conducting our trials inside the flash tank. And in industry, the concentrated liquid stream is usually the product, and when you have a multiple effect evaporator, this is the stream that would then be led to the next effect. In this case, we used a single effect. More theory. So these are some of the equations that we used. We have an overall mass balance, F equals L plus V, where F is your feed stream coming in, so the mass balance would be whatever comes in has to equal whatever comes out. So we have our feed coming in equaling the sum of what's coming out, L, our liquid product, and V, our vapor condensate product. We also have an energy balance equation where the unknown is our ST, or the mass flow rate of the steam, which we could rearrange this equation to solve for, knowing all of the other variables, F, again, the feed rate, and the enthalpy values. There's also a value SA, which is greater than ST. SA is what we actually measured in lab by, again, collecting the steam condensate in a small vessel, and then we could calculate the flow rate based on how much time elapsed during how much volume was collected. And this is because your SA is greater than your ST, because you're assuming that all of your steam is being evaporated, which may not be the case. And when we calculate through, we see that we use SA instead of ST because we're using what we actually calculated in lab. I'm sorry, what we actually measured in lab versus what we calculated. So the actual heat loss would be the SA, what we measured, minus the ST, times HS minus HC, which is the latent heat of vaporization, or lambda S, as I refer to it later in the heat transfer equation, which is Q equals SA times lambda S. The overall heat transfer coefficient, U, is given by, usually the equation is Q equals UA delta T, so we just rearranged this equation using the heat transferred as the numerator, divided by A, which is the area available for heat transfer inside the boiler, which was given and constant at 0.5 meters squared, times the temperature driving force, or delta T, which is TS minus TB, where TS is the temperature of the inlet steam and TB is our temperature of the boiler. So we did 2 different weeks, 2 different trials, looking at the effects, as Scott mentioned, on both flow rate and under vacuum or pressure conditions. So under vacuum, the vapor boils at a lower temperature, therefore less steam is needed to reach the desired product. You'll find that the economy is always less than 1 for a single effect evaporator. However, it can be greater than 1 for a multiple effect evaporator. And where you would use a single effect evaporator is when you have a small capacity or when the cost of steam is economical compared to the operating cost of the equipment. And one more slide of theory. So some factors affecting the capacity would be if the temperature of the feed is below the boiling point, some of that heat has to go into raising that temperature. Therefore, your overall capacity is reduced because the temperature must be raised in order for the boiling and the evaporation to occur or to begin. However, if the feed rate is above the boiling point, you may have flash evaporation, and that could result if your feed is above the boiling point. Some factors affecting the temperature driving force, which would also therefore affect your capacity. Again, the liquid feed temperature, and also the other 2 parameters that we studied, which would be the pressure and also the flow rate or the velocity of the liquid flow. So now I'll hand it over to Scott, who will talk about the apparatus and procedure.
The apparatus shown up here is the one we have down in the lab, and we only use the one on the right because the first one had been broken, so what we had to do was close any valves that would lead to the steam or the liquid into that evaporator. So we closed all those valves, and so that way it would only go through the left or the right half of the system. The way we collected our samples for steam flow and liquid flow was we closed valve 1 and opened valve 2 as shown in figure 3. And that way the steam could flow down, or the extra steam that condensed from the evaporator would go down, and we can measure it from the vessel that we collected it in. And then in figure 4 you can see the condenser, which we collected the vapor that evaporated off of the water. And that was collected down by opening valve 7, and it would lead out to our vessel again to collect it. And finally, the other part of the liquid flow that we measured was in the volumetric flask as shown in figure 5, where we would open valve 5 in order to let the liquid from the evaporator come out and see what we have for the liquid flow rate. For the pressure, in order to change the pressure for the second week, what we did was we closed the valve, which is where the yellow arrow is in figure 5. That way we would have a different evaporator pressure in the vessel itself. And we'd also close the other valves to the system. So we would close valve 6, which was open to the atmosphere, valve 3, which was open to the atmosphere, and valve 5 we would keep closed until we needed to collect the liquid from the condensate, or from the liquid or from the condensate over in figure 4. Whereas figure 3 we could just leave constant because it was already open to the atmospheric pressure. In order to collect the liquid flow, what we would do is close valves 8 and valve 7 in figure 4. That way it would close off the system entirely, and we would open up valve 6, which would open the system to the atmosphere, and we could collect it through the tube coming out at the bottom.
That was the relief valve. The purpose was to keep the rest of the equipment under vacuum while we were working on collecting our samples.
Yeah. In the same case with figure 5, where we would close valve 5, valve 4, and open up valve 3 to open it up to the atmosphere again. And then we would do the exact opposite process to put it under pressure again. And we would collect this steam and the liquid for 45-minute periods, collecting it whenever it filled up all the way. We would measure it at 15-minute intervals, but we would also measure the temperature and the pressure and the steam every like 7.5 minutes to 15 minutes, depending on what the system was. After 45 minutes, we would calculate the feed flow or the overall material balance to make sure that we were actually getting what the flow meter read on those liquid stream, and then we would calculate our enthalpy. Yeah, we would calculate the enthalpy change and the heat loss and the capacity and the economy for the system.
For week 1, the flow feed rates were 3.1 and 6.2, and for week 2, we had vacuum pressures of 60.65 and 11.72 kilopascals. So Scott will talk about the results from week 1.
From what we were expecting, the economy should have gone up, which it did as flow rate went up, because the economy is the kilograms of solvent vaporized over the steam feed. So this
water, the kilograms of water vaporized per steam feed.
For our case, it was water, and since the steam feed was constant and the flow rate went up of the liquid flow rate, we expected it to go up, and therefore more actually it did vaporize because more water was going into the evaporator and allowing it to vaporize more water in our case. And in the same case with the capacity, we would see the exact same flow or exact same trend because of the numerators were exactly the same in both calculating the capacity and the economy.
So I'll talk about the results from week 2. Just as a refresher, week 2 was where we had the system under pressure, under vacuum pressure. We can see from the graph, and again, there were only 2 trials run for each scenario, so possibly we could have seen a better trend if we had time to perform more trials. But from our 2 data points, we can see that as the evaporator pressure is increased or under less of a vacuum, our overall economy also decreases. This is because under a greater vacuum pressure, or to the left, the steam will vaporize at a lower temperature, therefore it's more efficient. under a vacuum versus under atmospheric pressure. And the same trend can be seen with the evaporator capacity. Again, because the economy is V over SA, or as Scott mentioned, the kilograms of water vaporized per kilogram of steam fed, the capacity is just V, or the kilograms of steam evaporated per hour. Also decreases with increasing pressure or less vacuum. So in order to have a better single effect evaporator, we found that running under more vacuum is more beneficial. Now Scott will cover the conclusion.
So as we've found out that our trends followed this, what we expected them to be in our theory. And so a higher feed flow rate equals the higher economy and the higher capacity. Whereas under the vacuum conditions, both the evaporator economy and the capacity increase as the evaporator vacuum was increased. So the overall pressure was decreased in the end. And some possible sources of error that we could have had was that the flow rate was not stable as we wanted it to be, because there was this really loud compressor or of some sort, or whatever that machine was. It ended up fluctuating the flow meter a little more than we expected, so it may have not been exactly what we wanted it to be, but that can be changed later on. And then the pressure of the steam was also fluctuating, and especially in the second trial. We're not exactly sure why at this point, but if that could be fixed, that would be better.
And there's our references. We had several handouts, and also our thermo book and our unit office book. And now we'll take questions.
Well done, guys.